record this. Okay, well, hello. Welcome to our webinar on basic DC electricity. Thanks for introducing yourselves. I just want to quickly make a land acknowledgement for the land that I am currently on. I'm in Oakland, California, which is currently unceded Lizjan territory of Hui Chin, now known as Oakland, Berkeley, Alameda, Piedmont, Emeryville, and Albany, California. The Confederated Villages of Lizjan are one of many Ohlone nations. Our local Indigenous women-led organization, the Sogorea Land Trust, have actually received solar suitcases from us, which is pretty cool. They're using them for some of their resiliency hubs around the Bay. And we have relationships with Indigenous groups around the state and also around the country. And personally, as an environmental science teacher, it became clearer and clearer to me as the years went on that learning about and using Indigenous wisdom is pretty key when we think about the challenges we're facing in terms of the climate crisis. And where I am in Oakland, land acknowledgements were becoming more and more common. So I'm trying to get into a habit of making them whenever I can. If you want to know more about whose land you're on, this is a link specifically for California, but I think it shows the whole planet. You can just Google Native Land Digital and find out more about the Indigenous groups from your area. Okay, I'm just going to copy a link to the slides because I always like having access to the slides. So if you want to have your own version of the slides, you can see them there. And I am going to just quickly go over our learning objective and agenda. So I try and use the 5E lesson plan model. You can click on the link if you aren't familiar with that and want to see how it works. I think it's just great. It really helps planning. It makes planning so much easier, and it really helps you think about how you are. It really fits in very well with the NGSS. So the learning objective for today, I'm trying to make it 3-dimensional in line with NGSS, is that you, teachers, will be able to describe and explain the relationships between voltage, current, and power by using mathematics and computational reasoning so that you can track how power is transferred between components in a standalone solar system. And this should meet basically all of our stuff really meets the DCI of energy, PS3. This one, everybody's favorite. I mean, I love trying to teach as much math as possible in a way that's fun. Using mathematics and computational thinking, SCP-5, and then scale, proportion, and quantity is the cross-cutting concept that best fits. And here's our agenda. So engage, explore, explain, elaborate, evaluate. It's gonna be pretty quick because we only have an hour. But we're going to go through the 5 steps with a quiz at the end, a couple of activities. Hopefully it will be engaging. I know it's super late where you are, Kanisha, so thank you. Hope I can, keep you awake. If you need help accessing our curriculum, I can hang on for a little bit at the end today, and I can help you with that if you need me to. I don't think the norms should be pretty easy when there's so few of us. But thanks for turning your cameras on. I really appreciate it. You feel free to use the chat as much as possible, although really you can probably just talk to me. That's totally fine. I don't think we're going to break out rooms because there are only 3 of us. It doesn't seem very sensible. Yeah, step forward, step back. Again, don't think that's that relevant with 3 people. And then keeping conversations student-centered is something I've added because sometimes when we're talking about electricity and solar, and people are really into the technical stuff, we can go off on all sorts of tangents, which are fun for us adults, but not necessarily helpful for, teaching an 8th grade student or whoever we're teaching. So try and keep conversations student-centered. Okay, here we go. This is our first section. So when I was thinking about how to engage you thinking about electricity, the fact that it can kill you is pretty engaging, I think. So I came up with 4 statements, and the question I have a poll for this. The question I'm asking you is, which of the following statements do you think is the most correct? I mean, you can argue that some of them are correct, but which one do you think is the most correct? I'll open up the poll while you're thinking about it, so that you've got time to think about it. Polls, where are you? Okay, I'm going to stop sharing for a second and see if I can open the poll. Oh, here it is. It's hiding. Okay. All right. Here is. Can you both see that? Yeah, I'll share my screen again as well. I was just hiding behind my. So the four statements we've got are: for a person to be injured or killed by an electric current, there needs to be both high voltage and high current. Second statement, it doesn't matter whether the current or voltage is high, it's the product of these two values, which is power. A high transfer of power will injure or kill you. Number 3, a very small current can kill you if it's pushed through your body with a high enough voltage. And then number 4, a large current will kill you even if the voltage is low. Okay, you've both answered. This is exciting. There's only 2 of you. I don't know who said what. Okay, so one of you said number 3 and one of you said number 4. Let me go back to my slides and share my screen again. Okay, I'm going to stop sharing. Does anyone want to explain why they chose the one that they chose? One of you is right. I mean, as far as my answer is, one of you has the same answer as me, at least.
I don't think mine is right. I think I chose the wrong one.
Which one did you go for? It's fine. We're all learning.
The last one, a large current can kill you,
Even if the
even
voltage
if
is
it's
low.
low. Yeah.
Did you go for number 3, Phyllis? Can you explain?
I went with that one only because you had that sign up.
Oh, I
so
did, yes.
Deductive reasoning, it says high voltage. So I was like, because I don't actually know the real answer to this question.
Yeah. So, I mean, when I was planning this took me I did a lot of thinking because I mean, electricity is invisible. We use it all the time, but there's a lot that that is it's mysterious. We can't see it. We know it's dangerous, but in what way is it dangerous? So I did a lot of research and I checked with the engineer that we work with just to make sure. But then, of course, when I did this with a bunch of physics teachers, they all argued with me about it. So, whatever. Electricity is dangerous. But this was the most correct answer as far as I could see, and I have evidence to back it up. So basically, what you can see on this table, these are small numbers, so milliamps, a thousandth of an amp. The first place we see death is possible is 50 to 150 milliamps, so way below half an amp. So a small current, and then obviously a larger current is more dangerous. So a small current can kill you, but your body offers quite a lot of resistance. You do conduct, but not very much. So the force of electricity is the voltage. So in order to get that current through you, you need a high voltage. So this is from OSHA, basic electrical safety. A statement I found was that 30 volts is generally considered to be dangerous. So when we're thinking about our solar systems, Kanisha, I know you've just kind of seen them, but Phyllis, you built them a few times, right? The small solar panel is we're dealing with a 12 volt system, so it's not too dangerous. But once we start wiring solar panels together, we can increase the number of volts quite quickly, which we'll get to a little bit later. So yeah, engaging. Electricity can kill you. And this is why. Great. Okay, let's do some.
My question,
yeah,
real quick, is kids will ask too. So you have the table on the amps, and then you said at least 30 volts have to be the pressure difference to make it really dangerous. But if it's 30 volts with a 1 milliamp, would it still be dangerous?
I don't think so, if the current is that low.
So you still have to have a decent current to
Yeah, right.
make it. It's not just the voltage. Okay.
Yeah, right. A small current, provided you have a big enough voltage to push it through.
So like a small current, you're saying like 50 to 150 milliamps.
Yeah,
Okay.
is what can kill you. And then once
Oh.
you're in the region of 1 to 4.3 amps, which is I mean, that's, you know, that's the kind of current that we're dealing with. Although often our currents are actually even lower than 1 amp. Then it starts to get really
But
dangerous.
they're normally more than 50 milliamps, right?
Yes, 50 milliamps is very low. Yeah. So for example, I guess if you're that's why if you're carrying a large solar panel, you don't want to be carrying it with it producing electricity and you holding both ends, because that could produce enough current if it's a large enough solar panel and it has a large enough voltage that it could actually cause you some damage.
Okay, thank you.
That's okay. Okay, so the math for this is nice and easy. I really like teaching this because, I mean, we all know that math anxiety is a real thing. And I've definitely found that when you can, and kids are terrified of word problems, which is science really, and engineering is just, that's what it is. That's what word problems are. So I think there are some great opportunities here to make word problems interesting and relevant, and then hopefully through that kind of increase confidence with math. We have a few years ago, we wrote curriculum for a summer program. We have tons and tons and tons of math questions. They're kind of at the end of our curriculum as an extra resource. So if you do want to dive into some more math, we've got lots of questions that cover different math standards that and also, you know, science standards and that relate to the solar suitcase and solar electricity. So lots of opportunities here. What I'm going to
like
do.
using the triangle for this when I teach it.
Yeah. Oh, great. You know what? Do you do that too?
Yeah.
I do that too. I did that last year with my 7th graders. I used to triangle and it worked pretty well.
Yeah, that's how I was trained in England. And I never saw it here. So I was like, oh, I guess people don't do that here. But maybe you do. So that's great. I loved it. I found it it's so easy to understand.
Yeah, kids that have math anxiety, they find it so much easier to understand it. They really like it.
Yeah. Great. Well, I don't have the triangle. Although actually I did make some curriculum when we went to Kenya. I created some curriculum for our installers to use when they go and install suitcases, and I have a whole bunch of triangle things printed somewhere. Okay, you know what? I'm actually going to just make a copy of this right now. I'm going to keep this blank because this one is on our curriculum. So I'm going to make a copy and call it webinar, and then we can I'll share the link with you both, and we can see. Okay, share. Anyone with the link can view. Okay, done. Copy link. Okay, so if you click on that link, hopefully you have editing abilities. And then you also have a copy of this. It's linked in the slides too if you want the original. I mean, it's basically just a worksheet, but it's on Jamboard. So, you know, different way to get kids to do some math. So if anyone wants to just complete any of those.
It says view only. I don't know how
Oh,
to
it does? Okay, thought I shared it so that you could.
Or maybe I just don't know how to edit on Jamboard.
Oh, it's because I shared the wrong. I did it wrong. Let's try that again. Oh, great. Someone else is here. Okay, that link should work. Hey, Clark. Does that link work for you guys? Is it editable, the second link?
Yeah,
Yes,
I
it
got
looks
it
like.
now.
Okay, great. Okay, you can have a race if you want. So yeah, the triangle obviously is great if you wanted to just, I mean, I'm sure you're both probably pretty good at math, but if you do want to write out the triangle, you know how to do that. Please go for it. Clark's just joined us. He is one of my colleagues. You want to say hi, Clark, while everyone's doing some math?
Hi.
Thanks for joining.
Yeah, sorry I'm running late.
It's okay. We're just doing some, well, actually, let me just put the link back in the chat for you in case you want to see what we did.
Thank you.
And if you want to try, I don't think you're going to get in there in time to compete, but you could try.
Actually really hard to put things in there.
Oh, it is. Are
But-
you using the
I was trying to use the text box. It was harder than I thought it was going to be to add the text box in there. But I got
yeah,
it.
Jambo's kind of funny. I mean, this is probably maybe a table isn't the best place to Jambo might not be the best place for a table, but it's pretty cool. Have you used it much with students? No. Do you use it with students? No. Did you both
No.
teach distant? Did you both do distance learning teaching? Yeah.
Yes, but we didn't use the Jamboard. I think I may have used it once, but that was a total flop.
Oh, really?
Yeah,
I was
'cause
teaching
it was-
seniors, so they're pretty good at that kind of thing. I think I
yeah,
used it
no.
quite a lot. I think I did. I mean, I feel like I did use it quite often.
These different ones where they wouldn't write over each other. Like,
Yeah.
see the comments for Padlet a lot.
Yeah. We use Padlet a lot too. Okay, well, I think you're getting them all right. I don't know if you two are people who actually need to really review this, but it's fine. And we'll come back to the drawing in a little bit. Is anyone going to do that last one? That's probably the hardest. You have to do division. Great. Thanks. Thank you. Okay, I'm going to go back to the slides. You can both use Watt's law formula, which is great. The answers are here. I'm pretty sure you got them all correct. Yeah, right. Those were, I think that was all right. Yeah, great. Okay, so I started with the numbers, which actually I don't think that's the way to do it with kids. I think it's better to start with this stuff with kids and then get into the numbers once they have a better understanding of the concepts. So I'm just going to go over this quickly, but we have slides that kind of go through and have questions, asking students to think about this analogy of using water to describe current and voltage. I've kind of combined everything onto one slide here, but in our curriculum, it's much more kind of slowly laid out. So here, the model that we're using is thinking of voltage as height of a waterfall, and then thinking of current as volume. Voltage is the push on the current, and then on the flow of electricity, and then the current is the amount that flows past any point at any given time. So that's one analogy that we can use. Another analogy that's pretty fun to do is to actually create a fulcrum and put something on one end a mango is here. I wouldn't recommend mango because I think that could get quite messy, although I think I have done it with fruit before. As like a soft toy, it's pretty good. And then if you can really like kind of go all out and do this properly, or you could just estimate. But if you have 2 different size containers, and you can kind of mark out heights, then if you drop the container, you say, this container represents 1 amp, and then the larger container represents another number, 2 amps, or in this case, 4 amps, and have them in comparative sizes. So a 1 amp container, a 4 amp container would be 4 times the size of a 1 amp container. You can use a bottle, just anything that I've used, containers like yogurt containers with dried beans in. You can use water, it might break. That's happened to me before, but that's just more fun. I've even seen one teacher, I probably wouldn't recommend doing this unless you really have a good relationship with your students. He actually had the kids like lie on the ground, and then he dropped things onto their backs and got them to say like try and work out what he was doing, which is a bit kind of pushing it, but they liked it. So, I guess he knew what he was doing. So yeah, if you have one height that you call a certain number of volts. So here we have 6 volts for half a meter, and then 12 volts for 1 meter. And each time you drop the container, you'll see the load fly up a certain amount. And you can kind of do some rough measuring, and you will see, what you would expect, which is if you double the height, you'll double the height that the load flies up pretty much. And then I don't think I would be brave enough to quadruple. I would probably double the size of this. Depends how high your ceiling is really, and what kind of a load you're dealing with. And then if you drop it, you will see the how much you'll see the difference that the equation would expect, which is the equation for power. So what this is showing is that when you multiply voltage by current, you get power, and as you increase either of those, you're going to increase the power. Do either of you have there are plenty of other analogies that people use. Have either of you used a different one for explaining this to students before, if you have taught this before?
I have not used the fulcrum analogy on the voltage and current. The way that I've broken down is because current is the word current. I get them to connect what is current based upon what they know, and current being like a stream of water or something like that. So I tell it how the water flows, and then I don't remember right now what I think for voltage, but they understand when I say about the current on it flowing through something. And I don't remember what I said for voltage, but they understood it, they grasped it, and I did not have to go really deep in trying to get them to understand the concept of electricity. I was actually pretty proud of them because of being able to teach Ohm's law to them as 7th graders. So
nice. That's great.
Yeah.
Very good. Do you have any of this, Phyllis?
Normally I use water.
Yeah. I mean, it's such a great analogy. So I've done this, we're not going to do this right now, but back on the Jamboard, there's a space. I've had students do this, and you know what? It was amazing. I remember these were older kids. These were like 10th graders, having them illustrate, just, copy what I've explained basically, but draw it themselves. It's a good skill to practice modeling, even if you've just been told what the model is. But then also giving them the option to come up with a different model. And I remember really clearly this one student basically herself working out the physics of a spring by using that as an analogy. Like, she worked out a whole other physical concept that we hadn't ever talked about by trying to explain voltage. So that was very cool. So giving the kids opportunities to try and model it, come up with the other analogies. You just never know. I mean, they might come up with something that needs a bit of help for it to make sense, but they might completely rediscover, discover something else that that's a physical concept that they work out themselves, which is always really cool. Okay, so that's voltage and current. Multiply those two together to get power. The next thing I wanted to talk about for the explain section is So in the 5E lesson plan, explain is where you apply the knowledge that you've covered in the explore section to a new scenario. And the scenario I've got here is when you start wiring solar panels in series or in parallel. I've got a couple of pictures that continue with the water analogy that show the two waterfalls in series and two waterfalls in parallel. And then pictures that show the what that looks like with solar panels and connected to a multimeter if you were going to measure the voltage and the current. Series and parallel wiring you may or may not cover, depends on what you're doing with the solar suitcase and what else you're trying to learn. But I think it's it's a real life skill for understanding electricity in case kids are going to go on and do this as a future career or a higher study. And I think it is a good opportunity to just really kind of push kids to think a bit further. Yeah, so what do either any of you think about if you were to wire solar panels in series or parallel, what happens to the voltage or the current or the power or any of those things? Does anyone want to try and explain using those images to help?
If I'm not mistaken, series will double the voltage and
Yeah.
parallel will double the current.
Yeah.
I think
Great.
I got that right. Yeah. Okay.
Yeah. Did you already know that, or did you work that out from the images?
I was trying to remember from what I learned over the summer, because before the summer I struggled last year with that concept of I couldn't remember which produced the double I needed to get a particular project working for a student. So we started okay, but I didn't have enough solar panels for what it was, and I was going off of memory from college, not gonna lie. And I couldn't remember we had it parallel and it was needed, but come to think about it, the circuitry needed to be both series and parallel for what we needed to do.
Yeah, I mean, you can get pretty complicated with the wiring. And then if you do have these small solar panels, it gets dangerous when you're using bigger ones, which we'll get onto in a minute. But if you do have these small ones, which if you don't, I highly recommend trying to get hold of them because you can just do so much with them so quickly. I mean, it really shows like the magic of solar that you have this tiny little thing you connect it to a tiny motor and it spins and then it's free. It's just going to keep going. So you can actually take measurements. We've got labs on that kind of at the end of our curriculum. Because you do need extra equipment to be able to do this, but it's really cool. You can do some math nice and accessibly. And yeah, just learn an application of what they've learned about voltage and current. What about power? How do these two methods of wiring affect power generation? Like, can you set? Yeah, go on.
The same? Wouldn't the power be the same?
Yeah. Can you explain why?
As far as the equation, you still have I don't know. I was thinking like the same amount of voltage and current. But I don't know. It just makes sense. I don't know
That's
how
good.
You're doubling one or the other, right?
Yeah, right.
So you're only doubling one of them and they're multiplying, right?
Yeah, exactly. So if you wanted to increase the power using a number of solar panels, you could use either of these wiring methods. But the next question is, thinking about what we talked about at the beginning, what would be the safer way to do that?
The second way, because it increases the current and not the voltage.
Yeah, exactly. If you start wiring things in series, you're doubling. Every time you add a new one, you're adding the same voltage again. So, and that, if you have a 12 volt, the small solar panels can produce. Yeah, well, actually, let me go to the next slide because I have pictures. I did this outside in my backyard and I measured everything. So if you can do this if you have these and check. It's a way if you have a suitcase, a classroom suitcase, and you have more than one of these solar panels, which some of our teachers do, you can wire these together to charge your battery more quickly or to have greater power to use during the day if you want to charge devices. But yeah, there's one way that's safe and one way that's not so safe. So if you do parallel wiring, which, I mean, if I go back a slide, you can see it's a bit easier to see here. Parallel, you connect the red wires together and the black wires together, whereas series, you make like a circuit, red to black, red to black. This is what it looks like in real life, but it's a little bit difficult to see. So if you wire them this way, parallel wiring, the voltage stays the same. And you can see, like, these are very small and they power a 12-volt system. But the voltage I'm getting here is 20 volts, which is, you know, quite high. You don't want it to get much higher than that. So a solar panel, we always use a solar panel with a higher voltage than the battery because we need to have that, you know, that slope, the push. Higher voltage has to push electricity into the battery. So yeah, the voltage would stay the same, but that you have the current doubles. Whereas if you do series wiring, does that say 42 or 0.4? I don't know. I have to look at my picture and zoom in a bit more. But if you wire them in series, you'll double the voltage, but the current will stay the same. So this is and as we learned at the beginning, the current, a small current with a high enough voltage can kill you. This is probably not high enough to kill you, but it could be high enough to hurt you. And it's a maybe not something to experiment with 7th graders, possibly, but it's fun, you know, if you've got some spare time and you've got these things and it's a sunny day, you know, you can take some measurements. And this is safe to do. I checked many times before I did it by myself in my backyard. I was texting Hal, who designed this, like, are you sure? Can I do this? Is this okay? Because this was all new to me too. Okay, great. So that's our explain section. This is a bit more challenging, hopefully, to kind of really get you to think a bit more, apply the knowledge that we've learned even further and elaborate on a totally new scenario. So in our solar suitcase, you can plug in one of these DC USB outlets. They provide a voltage of about 5 volts. And that's the voltage that pushes electricity into the device that you're charging, like a cell phone. The battery in the solar suitcase is a 12-volt battery. So this is being powered by electricity coming from a 12-volt battery that's going into an outlet that is going to send out 5 volts. So there's a question of like, well, what's happening there? So the question that I have is, if you've got a 0.5 amp current, 0.5 amp current running from the charge controller, so the brains of the solar suitcase, you've got 0.5 amp of current running from that to the load, which is this DC outlet. What current is being transferred from the USB charger to a phone, which is plugged into charge? It's quite a lot of information there. And if I were you, I would write this down. I don't think I could do this. Maybe you can do it in your head. I don't know. I don't think I could. I always have to write everything down. So yeah, I mean, we can also just kind of talk it through and see if you can work it out. So you've got battery with 12 volts providing a 0.5 amp current. And then what you get at the end on the other side is 5 volts and some other current. So what's the current that a phone is receiving once it's plugged into that DC outlet? And you can think of that in terms of there's something that stays the same throughout that whole transfer of energy. There's a value that we've talked about that remains constant.
Current that remains constant?
Sorry?
Is it the current that remains constant?
No, the current doesn't remain constant. It's something else. This is a hard question, isn't it? I spent a long time thinking about this. I mean, I spent a long time working it out. I've puzzled over this like a day.
my brain was going towards, because when I usually teach, well, when I taught electricity, I stayed on the resistance side of things and not so
Yeah,
much
right.
on the power.
We don't really get into that. Yeah.
Yeah, so this is kind of throwing me. I wanted to say something connected with the
Something about
consistency.
resistance.
Resistance.
Mm.
And I
Well,
don't.
what was the other thing you said?
56 watts of power.
Yes, yes,
Is that what
exactly.
remains
Yeah,
stable? Okay.
yeah. Can you follow that through?
So I
So you've
can
got
tell that it's 6 watts
Mhm.
going, and then the USB outlet. So then that means that it would be still 6 watts going
Exactly. Yeah.
into the phone.
hmm hmm
Okay. So it's the wattage that stays constant.
Yeah. Yeah. And that's how these systems work, is that I mean, it's pretty amazing that you can get into way more technical, complicated things that do this same transfer. You can change a voltage or a current while keeping the power the same, which allows you to just, use devices in different ways, charge things in different ways. So any idea what the current would be, or how you'd work that out?
Well, it'll be 5 divided by 6, right? For the current.
It would be 6 watts divided by
6 divided by 5
5
volts.
volts. Yeah.
Sorry, I just flipped my numbers.
Yeah, that's
I
fine.
don't have a
You're
pen
doing it in your
right
head.
Yeah.
You're doing what the kids do.
Oh, my
Like upside
calculator.
down, upside down, upside down.
Yeah. A
Yeah.
triangle drawn right now.
Yeah, so here are my numbers. Does that make sense? So this is what we get from the battery. So the battery into the charge controller, we've got 12 volts and half an amp, which is 6 watts. And then that power flows to the DC outlet, which is only producing 5 volts. So when I was thinking this through, I was like, hang on a minute, how does a cell phone charge when it's plugged into the suitcase? Because the current I'm reading elsewhere in the system is so low, and I know how big a battery is. It would take like 6 hours. But then I had this explained to me, which is that it's actually there's a transfer of voltage and current in the that's what the DC outlet does, is it lowers the voltage, which means it increases the current, which means that you can charge a phone in a reasonable time. So a follow-up question is a cell phone battery. We haven't really talked about this unit. And this unit doesn't really come up in, middle and high school science, but it can. I mean, it's, you can understand it. It's just getting a bit more technical, but it is how we measure battery storage. So a cell phone battery is about 4 amp hours, which means that it can provide a current of 4 amps for 1 hour, or 1 amp for 4 hours, or any other version of those. So the question is, how long would it take? And if you had an empty 4 amp battery and you have a current of 1.2 amps, how long is it going to take to charge approximately? Or you can actually work out. I don't think I actually have the answer. Let's do the math. How long would that take?
Over 3 hours?
How many was that?
Would it take over 3 hours? Because it would be 1.2 amps per hour, right?
Yeah, exactly. It's going to, let me get the actual number. Yeah, I got 3 1/3, 3.3 hours. Yeah. Oh, sorry. Yeah, so that's as far. I mean, you can keep going in this direction and get into way more complex stuff that maybe if you're teaching like 11th grade physics class, great, tons of stuff you could do, but most likely this is just for us to think about as the teachers. It might not be something that's that relevant for middle school kids, probably not. High school kids, depends, but it's starting to get a bit technical. But I think for me, when I was trying to understand this, because I had a pretty good understanding of electricity, but the specifics there were lots of things I was just like, hang on, I don't quite get it. And this was something I found really interesting. Hopefully others do too. I don't know. Okay, any questions about that section? Or questions about anything so far? Oh, I'm sorry, that was quick. Don't get too excited. No, okay, great. I'm going to, in that case, oh, we're doing great for time. I made a 5-question Zoom poll quiz. I know it's a bit stressful when there are so few people because they feel a bit exposed, but safe space. No one's going to judge you if you get something wrong. It's totally fine. So I'm going to stop sharing and I'm going to, you're going to do it, Clark? You're going to take the quiz? Okay.
I'll try.
Okay, there are 5 questions. Take your time. If there's a math question, you know, write it down, always helps.
I don't see it. Is something supposed to pop up on
You
our
can't see
screen?
it? Phyllis and Clark, can you see it? Yeah. Yes, it should pop up on your screen. Maybe it's hiding
it
behind.
just popped up on the front of my screen. It's just in front of your face.
Yeah, I'm not seeing it.
Did you see the other one?
Yeah, I saw the other
Oh,
one.
okay. It must just be hiding somewhere. I lost it mine earlier too. It'll be behind
Okay.
another
Yeah, do you have a second screen or something, or like other windows?
Yeah, I do. Let me.
I'm always losing stuff on Zoom.
See.
No, look.
No, the other one showed up just fine. Oh man. Ah, no, was
See
that it? No, that was the chat. Okay.
So these questions are all in our curriculum. We have just like 10 multiple choice questions that you can use however you want. We've put them on a Kahoot that is linked also if you ever want to use that. or copy and edit it. Sorry?
Is it linked in the PowerPoint?
No, it's not, but I can, let me find the link for you.
It'd be great to use.
I can't use Kahoot anymore because I'm not a teacher. So I don't really get access to much, which is a bit annoying, but we had another teacher make it, so we know that it works. Don't have that sweet district email with all the all the doors it unlocks to free stuff. Okay, let me find it. Okay, I've got, did you find it, Kanisha? Okay, that's fine. We'll just oh, the link I have here is for quizzes, but we do also have a Kahoot link. I need to add it on here.
Okay, I'll have
need
to
to get
search
it.
for it too. Do you know what it's called?
I think it's just called Basic DC Electricity.
Okay. Because that would be fun to do on like a Friday.
Yeah. Yeah, I thought it was in this document. I'll get it from the teacher who made it and add it in there. Okay, well, we can just go through. You won't be able to see these, unfortunately, I guess, Kanisha. But that's okay. Okay, so current is measured in amps. Yay, you both got that right.
Now I see the poll.
Oh, now you see it, now that it's ended.
Yeah.
Oh,
Yeah.
I'm sorry, I don't know. It's okay, we'll just assume you got everything right. Which one of these is an option? Which one of these is a multiple of 2 of the others? The answer is power, yay. if you have a 5-volt solar cell and you want to produce 10 watts of power, how much current do you need? 2 amps is correct. 2 times 5 equals 10. Force or push on electrons in a circuit is called voltage. Yes, great. And then number 5, if a solar panel is powering a motor with 20 watts and a current of 2 amps, what is the voltage? 20 watts divided by 2 amps is 10 volts. Great. Well done, Phyllis and Clark. You both got them all right. And Kanisha, I'm sure you would have done. Also, we'll assume you did. Okay, well, that is the end of my webinar. I just had one final question for you guys. I'll put it in the chat, but we can just kind of talk through it. You both seem pretty experienced teaching this, so I'm not sure. Hopefully you got something new from this, and maybe you've realized there are some places that you need a bit more review. I'm not sure, but are there any further steps you want to take to plan engaging lessons on DC electricity for your students?
I liked the new the fulcrum idea thing, the levers, and then I liked the waterfalls for explaining the parallel and the series. Like those were like at the beginning, I was like, oh, okay, this is all the same stuff that I do, but then those two things, I like that because I think that that's going to help them understand those two, because for some reason parallel and series is really hard.
Yeah, no, I agree. When I saw those images, we had someone who's working for us a few years ago make those, and I found them, so I was like, oh, this is perfect. I thought they're super helpful. Yeah, good. I'm glad that you like those. You have anything to add, Kanisha?
Yeah, I realized, well, the avenue I was going about doing it last year, again, I'm using my prior knowledge on being able to teach things just from my own education. And one of the things I didn't focus on was power, on wattage. I learned Ohm's law. I had to deal with computer components. So we dealt with resistance more. So I need to be able to incorporate that more if I'm going to. I definitely want to do the solar aspect of things too, because that was part of the challenge I had with teaching or even introducing solar. I knew about wind a lot more than solar, and I couldn't get certain aspects of it together, and wattage was one of them. I understood about the seal. Everything was just bits and pieces of things, and just needing to put that together more.
And understanding power. Let me just pull up the link so I can share it with both. Understanding power is super important because then it helps you understand energy. And energy is money. Like that's what we need our kids to understand so that they can read their electricity bills. Just finding my okay, I'm just going to show you this, but it's in our curriculum. I'll just share my screen one more time. I made this post. I've been working for We Share Solar for just over a year, and this was one of the things I did when I first started. Can you see that poster? You may have seen this before, I don't know, it depends when you train with us, but I only made it last year. It took me a long time. I was having conversations with people that knew a lot about solar and energy in general. They're just kind of throwing out numbers all the time. And I was like, okay, I need to write these numbers down and I need to put them on a poster because, you know, I grew up with like posters that look like this, but for distance, you know, scale, this is all about scale and proportion. So yeah, it would be distance or the electromagnetic, sorry?
Where can we find it?
It's in our curriculum in the language of electricity section. So I made a scale that shows at the top, you've got power production from small units of power to really large. So things like the state of California or a large hydropower plant. And then I have an energy production version as well. So the thing that there's stuff that we need to help our kids learn that we didn't. I mean, I didn't learn any of this stuff. Just like you were saying, Kanisha, when I learned about electricity as a student, it was all about resistance and building circuits yeah, with resistors and capacitors and stuff. And then when I came when I first came across WeShare Solar, I was like, oh, electricity, oh, it's so complicated. And I was like, oh, this isn't complicated. Once you're dealing with solar panels, I mean, obviously it can get more complicated, but it's so much more accessible than the stuff that I was being taught when I was a kid, I think. But the thing that we don't have yet in our kind of general, you can hang out with anybody and throw around numbers about distance or weight, and it's commonly known how to talk about those values. But we need, as a society, we need to be able to talk about, we need to understand quantities of energy and power, because both those things are going to be getting more expensive, and we need to understand how we're paying for them. And we also need to be able to compare, well, if we're shutting down this coal power plant, how, what are we going to need to, what are the numbers that we really need to understand in terms of energy use for communities? And, are we going to need to reduce our energy use? And we can't have those conversations if we don't really understand the numbers. So yeah, power. You reminded me a lot of where I was at when I first started doing this, Kanisha, when you said that, because I don't remember learning much about this at high school. It was maybe just an add-on at the end. It was all about Ohm's law and much more complex math. But this is really what power and energy is really what I think we need our kids to learn, so that they'll be just well set up for the future. That's my little rant about that.
I forgot the password to get into the curriculum.
Okay, do you want to hang on? I can help you log into that.
Okay, it just says this is content password, and I just need a password for the curriculum.
Okay, I'm just going to stop recording.